So in this video, we're going to learn about the law of conservation of energy. So if you've already taken chemistry, or maybe you're just familiar with this law, conservation laws are all sort of stated the same. And it is that energy can be neither created nor destroyed. It can only change forms. So we also have the law of conservation of matter, where matter can be neither created nor destroyed. It can only change forms. So really all of the matter and all of the energy in the universe is a finite amount, and it can only go from one type to another. So we've already learned about mechanical types of energy. And in this unit, we're going to kind of stick to just mechanical and isolate a lot of other things like friction. They can be thought about just theoretically, but we won't actually quantify them until later. So we have U, or our potential energies, and remember that we have two of them that we've talked about. So your gravitational potential energy, which is mgh, and your elastic potential energy, which is 1/2 kx squared. And then we also have the energy of motion, of movement, which is kinetic energy, which is 1/2 mv squared, right? So the idea is here that when we store energy in the form of gravitational potential energy or elastic potential energy, it can then convert to the energy of motion, and what is lost by one is gained by the other, right? And again, we're talking about mechanically isolated systems. So isolated systems where there's no friction. Because if friction occurs, then energy is lost in terms of heat. So understand this conceptually now, but mathematically we won't apply it. All right, so let's go ahead and just look at a very basic example. Right, so let's say I go to the top of a building and I have some object, and we'll just say it has a mass of like 3 kilograms, and the building is 20 meters tall. By going up to the top of that building, I have stored gravitational potential energy into that object, equivalent to mass times gravity times height, right? And we should have already done the problem where the girl is on a swing set, and we've seen her change in gravitational potential energy relative to her height, where she's at the top of her swing, mid-swing, and at the very bottom. So we know down here that the gravitational potential energy here would be 0. So all of the gravitational potential energy that I have stored in this system of the ball at the top is really the total energy in this system, right? Would be the maximum amount of energy, quantity of energy that would ever be had. If I were then to release that ball, we know from our very first unit that it starts to fall to the ground and it starts to gain speed, and we learned all of our constant acceleration equations, so we could calculate how fast it was going at any point or at any height. And now we're going to use the idea of gravitational potential energy and kinetic energy and conservation of energy to quantify those things, which is much easier, right? So as the ball falls, it starts to gain velocity, and therefore it starts to gain kinetic energy. So the conversion that's happening is going from GPE to kinetic energy. And because energy is completely conserved, it means all of the energy that's lost to the form of gravitational potential energy becomes the kinetic energy form, right? So up here at the top, let me just calculate it out. I have 3 times 20 times 10, that's 600. I don't even calculate for that. So at the top, I have a total of 600 joules, right? That's the total energy in the system. So if I release this ball and it falls down to the ground, and at the ground it has 0 height, therefore 0 gravitational potential energy, that means I can say that all of that energy has become kinetic energy. So at the bottom, this object has 600 joules of energy. And then at any point, I can, measure and see, how much has the height changed, therefore how much has the gravitational potential energy changed, where has that energy gone? It has become kinetic energy. So if I select a position, say 1/2 of the way down, so at a height where h equals 10, then I would say, okay, well, 1/2 of the energy is gravitational potential energy, and 1/2 is kinetic energy, but they will still, if I add them together, would be equal to the total, right? So 1/2 of GPE would be 300, and then that my KE would then be 300, and then total would still add up to 600. So if we take a look at this, this is a simulation on FET. Here, let me open. I like to see the bar chart. So you can see here it includes thermal energy in total. But if I were just to take this person and, oop, I've dropped him. I want to put him on the ramp, right? And see that where he starts at the top, you have his total and potential energy being equal to one another. And then as I release him, you'll see in slow motion that his potential energy slowly becomes kinetic energy, but his total energy does not change. So as he falls, one goes up, the other goes down, but total energy stays the same the entire time, right? Now, if I put him on some different looking ramp, you can see as he slides down, he will be gaining kinetic energy and losing potential energy. And then as he goes up the hill, he regains potential and then regains kinetic and then regains potential, right? So, but the total energy is never changing the entire time. So it's just an exchange between kinetic and gravitational relative to his height above the lowest position. Okay. So let's go back and actually we can perform some calculations. So let's see here. We used to be able to, I used to give you problems like this where I'd say somebody drops an object off of a cliff, how fast is it going when it hits the ground? And we'd have to use VF squared equals V initial squared plus 288. But here, now we have another simpler way of doing this where we can use gravitational potential energy to set this up instead. So what is the velocity here at the bottom? Right, that's my question. Well, I already know kinetic energy is 600 joules, but let's set it up using conservation of energy. So what I would say is that the gravitational potential energy total, or excuse me, at the top we'll say, has got to be equal to the kinetic energy at the bottom, right? Because one form has completely become the other. So in this case, you can see that mass actually cancels out. We don't even need mass in order to solve this problem. So I would have G times H, so 20 times 10, and then divided by 1/2 B squared, so that'd be 400, square root of 400 is 20, so 20 meters per second. And we know that mass does not affect how fast an object falls, so it makes sense that the mass cancels no matter how no matter what size that object is, it should still hit the ground with the same velocity. Right? Now, I could also easily figure out, well, let's say it has fallen 13 meters down. So that means now it is only 7 meters above the ground, and there has been a change of height of 13 meters. So what I could say is that at this position, at the beginning, before, all of the energy is gravitational potential energy. Then at the end here, some of it is gravitational potential energy and some of it is kinetic energy, right? The difference between these two numbers, these two heights, tells me how much kinetic energy I have gained, right? So the amount lost here is equal to the amount gained here, right? So I could set that up and say, well, the difference between the MGH here and the MGH at position here, so we'll call this at the top and at some position 10 meters, or 13, sorry, meters later, has got to be equal to the kinetic energy that that object has at that position. So the difference here is going to be equal to KE. Well, the difference is 13 meters worth of gravitational potential energy. So I'm just going to do mass, which is 3 times 10 times 13, which is my change in height. Okay. It's got to be equal to 1/2 mass, which is 3b squared. And again, the masses actually cancel out. But I could then just solve, and I have 130. So the square root of 260, whatever that happens to be, is the velocity. Let's just plug it in and see. So about 16 meters per second is how fast the object is going there. Right? Now I could also say, well, how much kinetic energy does it have there? Well, that would be equivalent to this, which would be 130 times 3, 390 joules of kinetic energy is the energy that that object has there. And then I could also state that, well, that means that there has to be 210 joules of gravitational potential energy at that position, because remember, the total would always have to add up to 600, right? So we're essentially just taking the idea of gravitational potential energy and kinetic energy and converting from one to another. Now, what's cool to note about this is when we're dealing with frictionless inclined planes too, which is this is what you're actually going to be doing in the lab. When you have a frictionless inclined plane or a loop or whatever, we used to have to figure out, okay, well, what's g sine of theta? That's going to be my a. None of this is important anymore, all right? So I can very simply figure out how high above the ground that inclined plane is by making it a right triangle, and I can just say the gravitational potential energy up here is equal to the kinetic energy down here. Okay, so a lot easier than using our constant acceleration equations. But again, remember that this has to be a frictionless surface for that to work.